Hello, my name is Eric Brasine, and along with Evan Hassman, I created the Smart e-bike. So, e-bikes are great. Compared to cars, they're cheaper, better for your physical health, less dangerous, not as bad for the environment, and arguably more fun, especially if you're stuck in traffic. But they're still pretty expensive, as in $2,000 to $10,000 for a good one. Essentially, in this project, we want to produce an alternative that a college student could afford. It should include a motorized pedal assist, a fully integrated bike computer, and other cool features such as blinkers. So, how did we do? The Smart e-bike is capable of cruising at 9.5 miles per hour. It has a 40-minute battery life, which definitely could be improved, but it'll take you to and from class. It displays accurate readings of speed, temperature, altitude, time, and more. And we spent about $100 on this project, while all the parts new would run you around $350. It's also way more fun to ride than it sounds like. Look at how happy this guy is.
Hello, my name is Evan Hassman, and I worked on the motorization of the e-bike. This included the wheel driving system, as well as the power system to give the motor power, as well as the physical attachments that attached all of the parts, the motor, the batteries, and all that to the bike itself. I also provided the Toro 51618 leaf blower. The externals were heavily damaged throughout use in my family, but the electronics were still very salvageable. And I provided the Mongoose bike, which was found in the backyard of the house that I'm currently living in when we moved in. It was incredibly damaged, but we decided it was still capable of being ridden safely. My primary goal in the project was to motorize the e-bike. I used the leaf blower's original circuit, which included the speed selector and a safety pin that we used as an enable, as well as I created the motor flywheel. It was a PVC cap that was attached to a pronged T-nut, and as well as some washers and bolts that we attached directly onto the original leaf blower's motor. Our first attempts on the project involved using the e-bike throttle connected to the bike computer that would regulate the speed of the motor. However, we decided that this was too expensive in both time and money, and we decided to use the original circuit with some minor modifications to fit the power source that we provided for it. You can see the circuit here. It uses a safety switch that we decided to use as the enable pin, as well as a speed selector. The speed selector will reroute the power through the Zener diode, which reduces the voltage of it or the speed, or it will place it into a faster mode where it goes directly from the batteries to the motor. And then the third position is disconnected, which is just an off safety switch. Our first attempt to power the e-bike involved using a UPS or an uninterruptible power supply. Unfortunately, we were not able to provide enough current to the motor due to the safety features on it, which is a breaker. So we decided to switch to the batteries that we had in the lab. As part of Rambots, we had some 22.2 volts 100C lithium polymer batteries available to us. They don't include any sort of safety materials, so we didn't have to worry about tripping any breakers, and it was also able to provide just enough current to move the bike while someone was on it. We also created the wire connectors to use two of these batteries in parallel. One battery is capable of providing about 20 minutes of the battery life, so by doubling it up, we could effectively double our power output, or our power supply, which would take it to about 40 minutes total lifetime. We made the parallel battery adapter by ourselves. Attaching all the components was a little bit difficult. We didn't have any mechanical engineers, nor my mechanical engineer, so we did our best. We used a lot of zip ties and a lot of scrap wood, nuts and bolts from Home Depot, and the final product ended up having surprisingly good adhesion to the wheel itself. We tried using sandpaper to actually increase the adhesion, but because of the old hard rubber tires, we ended up damaging it more than providing any assistance.
I was in charge of the bike computer subsystem of the Smart e-bike. This is the system that makes our Smart e-bike smart. Its job is to capture and convey useful information to the cyclist, such as speed and elevation. Also, it has blinkers you can activate with the press of a button to help ensure the cyclist's safety. Note that the foundation for this project was a primitive bike computer I designed for EC202. From that project, I have reused the Arduino Mega, the display, and the Hall effect sensor, but the code and circuitry is entirely new, and I've also added a lot of new hardware and features. Here's an overview of the display. We'll soon go into greater detail of all of these values, but for now, in the top right, we have the speed in miles per hour. We calculate this using a Hall effect sensor to measure every rotation of the wheel, and then we can use the change in time between those measurements and the tire circumference to calculate the speed. Second, we have total distance. This we can get really easily as the number of rotations times the tire circumference. Third is the ride duration, straight from the Arduino Mega's internal clock. Fourth is temperature, from our barometric pressure and temperature sensor. Fifth is elevation, which is calculated from the air pressure retrieved from the same sensor. Sixth is real time, which we get from our GPS module. Seventh is whether our blinkers are active or not. And eighth is our revolutions per minute, calculated very similarly to the speed. Now we'll go into each piece of hardware and why we picked it. On the right, you'll see our overall schematic with the component we're talking about highlighted in red. First is the Arduino Mega. Arduinos are usually a pretty good choice for budget embedded systems projects, but we opted for the Mega specifically due to its increased I/O power and capabilities. It has a 256 kilobyte flash memory, of which we use 33%. Also, it has 54 digital I/O pins, of which we use 39. Next is our LCD, or our thin film transistor liquid crystal display. This thing is colorful, fast, and affordable, but most importantly, it's designed specifically for the Arduino Mega and sits on top like a shield. That makes it very convenient to connect and use. Our Hall effect sensor is mounted on the frame of the bike to measure the magnetic field of a magnet rotating around on our tire. You can buy several of these sensors for less than $1, but they're actually very effective. The circumference of a bike tire is standardized, so if we know how many times our tire is rotated, we have a near exact measurement of the distance we traveled. These are our NeoPixel Joules, which are rings of individually addressable RGB LEDs that are very, very bright. We have 2 of them on the back of our bike and 2 push buttons on the handlebars to activate them as blinkers. We have them running at 50% brightness right now, and you can see in the picture that they're perfectly visible in daylight, almost as bright as the car's taillights even, so pretty good stuff. This is our barometric pressure and temperature sensor. It's pretty affordable and effective for measuring temperature and air pressure. It also supports I2C, meaning that it's very easy to hook up. The main downside for our purposes is that, even though I'm trying to use this thing as an altimeter, it's not an altimeter. I'm converting air pressure to altitude, which isn't as accurate as buying an actual altimeter, so in retrospect that's what I should have done, but it serves its purpose well enough. Last is our Neo 6M GPS module. I selected this sensor because I knew it could collect a lot of decently accurate positional data. The one major downside is that it requires line of sight to satellite, so data transmission is pretty unreliable for our purposes. We decided to only use it for the real-time clock for now, but in retrospect I would have replaced this with an actual real-time clock module. Now, a little bit about our Arduino code. Here's a software flow diagram depicting all the major functions. We begin up here in the setup, where we establish connections to all of our devices, then we enter into our loop. Before that, though, if you look on the right, you'll see our interrupt service routines. These handle readings from the Hall effect sensor and push buttons as quickly as possible to avoid timing issues. They just set flags that are handled later in the main loop. In that loop, every iteration, we check if the Hall effect flag has been triggered. If so, we run our calculations and then update the display. The other part of the loop takes place once every second, and this is so that you can't see the display flashing constantly. We update the ride duration every second, the temperature and altitude every 20 seconds, then handle the blinkers if their flag has been set, and handle the GPS if GPS is available. I tried my best to follow the coding methodologies we studied in this class, so feel free to take a look at Appendix A and C. Back to Evan for future work.
While we are very satisfied with the end results of the project, there's still a lot more to be done with it. For example, the sensors that we have are various states of disarray. The GPS, which is used for displaying the time on our display, takes about 6 minutes to find the satellites that are required from it. And the pressure temperature that we use for reading the temperature as well as determining the altitude is very good at measuring the temperature, but the air pressure is only partially used to determine the altitude because various atmospheric changes can modify that. So if we were to combine these functions onto one chip, one with better ratings, we could perhaps have more accurate and more reliable information, as well as a easier maintenance and better user experience. Another big improvement to be made is the power situation. The batteries that we ended up using are very expensive. They're about $150 for 2 of them, and they're not strong enough current-wise to be able to power the motor unless it was given a little bit of help. The motor is able to maintain speed very well, up to about 10 miles an hour, but from a dead stop, it will not be pushing you anywhere. The motor was also designed for a 120 volt wall outlet and not the 22 volts that we are providing it, so a better power source would be able to push the motor faster and obtain a higher max speed as well. The original bike that we used was not the ideal choice. It was once again found in the backyard of my house when I moved in. It has lots of issues with it, including one brake in the front. These brake pads that we're using are also old and brittle. The gear shifts are completely removed and damaged. It's also very badly out of tune. There's lots of squeaking, and the back wheel specifically is an oblong shake, which makes the motor not adhere to it the whole time. And on top of that, we believe that it is a child's bike due to the size and the uncomfortable riding of it. It would have been nice to have a better attached project. The current version of the bike is functional and will not explode in any sort of disastrous manner. However, small things that can break, zip ties and such, will reduce the adhesion of the motor flywheel to the wheel itself, which will reduce the ability for it to push. This is an issue that we have experienced before and that we will fix in the next version. And besides that, the controls are loose and will slip under your finger. The zip ties that are used to attach them are not properly adhered to the bike frame itself, so they will slide around, making a kind of uncomfortable user experience. And the button that is the accelerator, or the enable switch, is designed to be pressed by a plastic prong that sticks out of the motor or the leaf blower itself, and this will hurt your finger after a while because it's not designed to be used by a human. A good fix to this would be 3D printed parts. If I had the skill set to do so, I would have modeled them and printed them out, and unfortunately, I do not have that skill set. All, this project was a great learning experience for some real-world applications of embedded systems. We learned specifically that embedded systems take a lot of time and money. High voltage power is very complicated and potentially dangerous. I did shock myself a couple of times, and I learned very quickly not to do that again. The motors that we're using, I was not expecting them to take so much power, and it was hard to supply the motors with those power. And then choosing the right hardware the first time is very difficult. We had lots of trips to Home Depot that could have been avoided, as well as a bit of unnecessarily spent money. Writing particularly timed software with interrupts and shared memory is a very challenging feature. And then the biggest part that we learned is to do more testing. Thank you very much for watching this presentation on our EC561 Smart e-bike.